I'll get started. I hope we do not have much interruption. All of you are able to see my slides.
Yes, sir. Yes, sir. We can see.
Okay. And okay, I hope everything is intact. You are able to see the entire screen. If not, please let me know. I hope all of you are seeing the first slide, right? Yes?
Yes, sir. For me, yes. Yeah. I mean, I can see the chat box. It is yes. I request participants to unmute yourself and say the answer. Then only sir can hear it. I think while sharing the screen, he is not seeing the chat box. So it's
Yes,
my
I only
suggestion.
see my PPT, nothing
Yeah.
else.
Yeah. So my suggestion to the participants, please unmute yourself and say the answer rather than putting into the chat box. Anyway, sir, please carry on. It is visible. It is clear. Perfect.
Okay, it's clear. And if there are any comments also, I think it is better to either directly message me if I get a chance, or any moderator can bring it to my notice, because I don't see chat box also during the presentation. Okay, otherwise, how are you guys doing?
Yes, sir. Fine, sir.
Doing great. And do you have any doubts in the last session? Anything we have to address? It cannot wait till the end of the session. Please let me know. Otherwise, we will get started. And I just want to cross check once again. All of you are able to see the second slide also, right?
Yes, sir.
Okay, perfect then. Then everything is going good. And last class we discussed about that why electromagnetic spectrum is extensively essential for any spectroscopic technique. And then under the solid state NMR, we discussed about solid state NMR and some of the lipid nanomaterials we discussed. And today we will discuss little more about nanomaterials or biological systems, and then shift our gear to the inorganic materials and ferromagnetic materials also. Just as a recap, okay, all of you know that NMR is basically a nuclear Zeeman effect. Okay, once we insert my sample in the RF coil, and if I keep my RF coil in the presence of magnetic field, okay, then the energy level associated with the magnetic nuclei that would get separated. At the same time, if I shine that external radiation, I hope all of you are able to see the entire screen.
Yes, sir. Yes.
Okay.
Yes, yes, sir.
Yes,
Okay.
sir.
And whenever we do that, at the end, in the sense, now energy levels get split in the presence of magnetic field. At that point, if I submit or if I send right amount of energy, transitions do happen. That transition somehow gives my free induction decay, that is the NMR signal, that will be Fourier transformed to see our conventional spectra. Okay, this is our conventional spectra. Basically, it is one of the first observation of the chemical shift. They did it in, probably, as you can see, that it happened, actual NMR spectrum, they observed it in around 1945 or so. Okay, he is one of the pioneers in this block. He developed NMR theory also. As most of your chemists or biologists, you know that this spectrum, all of you are able to see. Why are we getting 3 peaks here? Yes, any quick answer?
Three types of
Three
proton.
different.
Yes, though it is a NMR signal of one particular nucleus, that is hydrogen, because we have different hydrogens which are having different kind of chemical environment. That's why we are getting 3 distinct peaks, this observed in the early days. And now if you go to any modern spectrometer, you would see that that individual peak is comprising of several other peaks. That's what in your first few sessions, they have talked about that, how to analyze this kind of NMR spectra. Okay, as I mentioned it in the last class, I do not spend much time on that. Okay, here our conventional NMR spectrometer or NMR resonance, nuclear magnetic resonance, basically probes the nuclear spin system, and that is subdivided into three parts as I explained in the last class. Okay, one is solution state NMR, solid state NMR, and MRI imaging. And solution state NMR basically used for structure and to structure, I think again. Okay, here, okay, somewhere they are getting mixed up. Okay, it's okay. Yeah, somewhere something has happened. Okay, now we know that my entire session is restricted to solid state NMR, where I need to study about the dynamics and structure. In the last class, we paid more attention towards the structure. That structure can be studied by measuring the line shape function or line shape of the NMR signal. And today I would be concentrating more on the dynamics part of that. How can I measure the dynamics associated with the given material? Okay. And as we know that, can I do NMR for all nuclei? Probably no. That is because of these standard systems or standard rules where if I want to observe NMR, I need a net magnetic moment. Okay, that I should not be equivalent to 0. Okay, whenever I is either a half integer or full integer, then I can do NMR. Okay, from that I also explained about that. This one, this particular slide, I will come back at the later stage. What is conventional NMR? What is internal field NMR? Let me hold it for a while. Okay, that time we will try to discuss this concept again. Okay, first let us try to understand conventional NMR with dynamics. Okay, and why we are not able to do NMR of all the nuclei, though even some of the systems are having non-zero nuclear spin quantum number, even then we are not able to do NMR. That is because the sensitivity of the NMR signal, or whenever I record the NMR signal, if it is less sensitive, again we have problem. That's why people talk about different, they started increasing the operating frequency of the NMR spectrometer. Okay, earlier the spectrometers used to be 600, used to be the very good spectrometer about 10-20 years ago. Nowadays it is going beyond 900 megahertz. Okay, and as price, as the operating frequency, I think all of you know that 800, 900 means it is corresponding to hydrogen nucleus. Okay, what is the magnetic field required to magnetic field being applied? Okay, to make my hydrogen nuclei revolve around the static magnetic field with the frequency of 800 megahertz. Okay, that kind of magnetic field or superconducting magnet, we call it as 800, and that along with the entire spectrometer, we call it as 800 spectrometer. And similarly 900 spectrometer, and you can see that funny or much more sophisticated NMR spectrometers are being installed at national labs, institute, as well as National High Magnetic Field facility at Tallahassee, Florida. Okay, and as you can also see at the bottom, the number, this vitamin M, the price also goes up as you go from one spectrometer to higher frequency spectrometer. Whenever price goes up, okay, obviously as a end user, we have to start paying more money to utilize this equipment. Okay, hence whenever I want to study complex systems, okay, or less sensitive systems, I have to go for highly sophisticated equipment. That is one of the limitations all of us do have whenever we come from local institutions where we do not have all the facilities. But nevertheless, but still most of the nuclei we are able to do it. Okay. Now, my entire talk, as I mentioned that yesterday I talked about the solid state NMR of lipid membranes. Okay. And today I will try to touch upon membrane proteins as well. Okay. And then we shift our gear to inorganic materials and internal fields. Okay. Now, as we discussed in the last class, we know that cellular membranes are made up of lipid molecules, and these lipid molecules form this kind of bilayers, membrane bilayer. Through deuterium NMR, we will be able to measure all the parameters given in this particular unit cell parameter. And once I know this cross-sectional area and acyl chain length through NMR, that can be utilized to extract some of the mechanical properties associated with membranes also. And along with that, I can also measure different types of motions happening in the entire membrane system. This kind of a viscoelastic membrane deformation that happens in the order of milliseconds. Okay, that can be measured with the NMR relaxation time measurements and NMR spin lattice relaxation time measurements. I can measure the molecular diffusion associated with that. Whenever we have fast motions for us, okay, fast motions, because they require only 10 to the power of minus 12 seconds to make one motion. Okay, that can be, whenever we want to study that, I have to rely on not only the NMR, some other associated techniques I need to understood or I have to explore. Okay, let us try to connect all of them through NMR window in a while. Okay, now this one, it is just a recap. Okay, we discussed in the last class, deuterium NMR gives two peaks, and the distance between left side peak and right side peak, the difference gives the residual quadrupolar coupling constants. Okay, before that I assign the peaks, and once I get the residual quadrupolar coupling constants, I can measure the segmental order parameter. Okay, that is SCD, and that is basically directly proportional to the distance between these two peaks. Okay, and once I know this SCD values, I can calculate what is the cross-sectional area and what is the chain length of the given lipid molecule in a membrane structure. Okay, and up to this point we had discussed at length in the last class, and we also discussed that why it is important to study. Okay, once we study this kind of molecular structure, okay, and if I vary one of the parameters like pressure or temperature, okay, one can measure some of the intrinsic properties associated with the lipid molecules. Okay, what are the pertusion forces happening, and when do we get undulatory motions happening in the given system? Okay, that can be explored, and from that kind of work, whenever I apply dehydration pressure or osmotic pressure to the system, and then I can monitor how area, cross-sectional area or area per lipid would vary as a function of pressure. That would enable us to calculate some of the energetics associated with that. How much energy is required to deform the body can be measured, and these would help us to understand several pressure sensitive proteins or mechanosensitive channels, what you study in biology. Those can be understood by performing these types of experiments. Now, same thing, whenever I consider, we know that my entire biological membrane consisting of not only lipids, some portion of cholesterol will be present, some part of detergent would be present. Now we just explored, or we tried to explore what would be the effect of osmotic pressure for these kinds of lipid mixtures. Okay, and when we added detergent to the pure lipid, we saw that the distance between these two peaks got reduced. As you can see that when I change this is the original combination of detergent with my model lipid DMPC, it got decreased. Then we started applying osmotic pressure to the system. That's what the bottom line, this blue line on the right and brown line on the left, both are one and the same. At that point, when I started decreasing the number of water molecules per lipid, then again they start increasing. The distance between these two peaks start expanding. That tells that my membrane swelling is happening whenever the detergent is added. Nevertheless, for the similar type of system, whenever we have a membrane with only lipid and cholesterol, and for that, when I start decreasing the number of water molecules per lipid, that is basically what I am seeing from the bottom to the top is what I am doing is I am increasing the osmotic pressure. Okay, osmotic pressure will be increased when we decrease number of water molecules associated per lipid molecule. Hence, whenever we added cholesterol, we can see that it is the distance between these two peaks got increased, because by default cholesterol increases the distance between these two peaks. That means that they make cholesterol more rigid, or they may, in the sense, cholesterol make my lipid membrane more rigid. That's why you may not see much variation here. Okay, but it is still varying because I am coming to the extreme length here. Okay, this is one type of, for the biological applications, if I want to study with specific goal, I can make use of this deuterium NMR. Now, let us come back to the dynamics associated with that. I think anyone has performed this relaxation time measurements so far? Yes, guys? Anybody
No,
has
sir.
done? No? Okay. This is again the relaxation time measurements would help us to understand, okay, what type of motion is happening in the given material. As I told you that whether segmental deformation is happening, okay, acyl chain motion is happening, that type of different regimes of motions can be studied by measuring relaxation time measurements or relaxation rate measurements. Okay, one is by, probably all of you are familiar with this line shape function. That line shape function, in your conventional way, you measure it as a function of chemical shift. Okay, how chemical shift changes would infer the changes in the chemical structure. In the same way, the change in the relaxation time or variation in the relaxation time as a function of frequency or temperature, if I do, I can measure or I can extract what type of dynamical processes are going on in a given material. This is one of the representative pulse sequence. I think all of you would have been using whenever you apply. Any of you have operated NMR spectrometer per se? Or you have just submitted the sample and you got the spectra?
Yes, sir.
Anyone has operated NMR spectrometer? Okay, if you are not, okay, let us not spend much time on that, but you can measure the relaxation time using these kinds of pulse sequence, okay, inversion recovery pulse sequence or quad echo pulse sequence, and this intensity of the NMR signal, okay, this intensity, the peak maximum position intensity as a function of this tau whenever we measure it, okay, then the signal intensity initially will be in the negative direction, and then as tau is increased, it goes to the positive direction. Approximately, I can estimate what is the relaxation time. That is basically a spin lattice relaxation time. It is called as how much time your atom stays in the excited state before it comes back to the ground state once you excite the given molecule, or once you excite the atoms in a given system. Okay, that is what we call it as relaxation time. Okay, and once I know the relaxation time, they are interconnected with the spectral density associated with the given molecule. What do you mean by spectral density? Please do not get distracted whenever you see these kinds of complex equations, because I am a physicist. You don't believe me if I do not show any mathematical expression that I am a physicist. That's why I am showing this. They are not much complicated, complex. Okay, they are very simple. But since the mathematical derivation requires us to calculate or incorporate what are the different types of motion happening, okay, I have to include 2 terms or 3 terms. Okay, one we call it, the top one we call it as spin lattice relaxation time measurement. The bottom one is called spin relaxation time measurement. As you can see that the bottom one has 3 terms. One is J of 0, J1 of omega, and J2 of 2 omega. Basically, omega naught is your operating frequency of the spectrometer. Okay, whenever the motion is happening here, the same time scale of the operating frequency, then if I measure this R2 measurements or R1 measurement, I can extract information related to that type of motion. Okay, for these lipid molecules, it looks much more complex. Just ignore the complexity associated with this entire whatever the equations I have written. Okay, what the take home message, what you need is I can make relaxation measurements for any of your systems, okay, using these kinds of pulse sequences. Okay, and then once I have this relaxation time measurements, if I plot this relaxation time as a function of bond order parameter, what I showed it earlier, okay, they give a square line, in the sense linear graphs. Okay, those linear graphs would explain that what type of relaxation is happening. As it is given at the bottom, the spin lattice relaxation rates follow functional square law at low and high hydration levels, indicate dominant collective dynamics, in the sense how what type of motion is happening in our system. What is given by or after studying that, what we got is that we did not see much variation in the R1Z measurements. Okay, that is spin lattice relaxation measurements. I did not see much variation from as I increase the water concentration. Okay, but same thing whenever I did spin relaxation time, where the slow motions can also be measured effectively, then we started seeing that it deviates from this linear fit here. Okay, whenever these order parameters are increasing, that means that at that point, okay, they are deviating from that. That would help us that the penetration depth of the water decreases with decrease in water due to undulatory motion. Okay, and in the sense the take home message or simple message what I can take from these graphs is that I can measure, I can distinguish what type of motions are happening in the given molecule by measuring this spin and spin lattice relaxation times. Okay, now let us talk about this membrane proteins. How many of you are there from hardcore biologists? Do we have reasonable strength? Okay, all of you, I hope some of you, it might be very wonderful topic. Please go through the whatever the papers I have quoted at the bottom to understand it more. I quickly summarize what our previous lab, other members were prominently working on that. Okay, here membrane protein. Okay, one of the example what is well studied is rhodopsin. Why it is well studied? Because it is one of the recognized, okay, G protein couple receptors. Okay, it is well defined with well defined membrane system. Okay, and once I study this, the functioning of GPCR, for example here rhodopsin, that would help us for our drug industry. Okay, and we can measure for molecular dynamics simulation work, what you see computational chemistry guys, they do. Okay, the information associated with this kind of GPCR is extremely useful for them. Okay, rhodopsin, as you know that it is present in the rod cells of our retina in our eye. Okay, and they are responsible for vision in dim light conditions. Okay, and it is one of the well recognized GPCR. as you can see that your rhodopsin, the small portion, if I expand it, it looks like that. Okay. And this entire system is in this particular fashion. What I have blown up is only small portion of this disc membrane, where the central one is our membrane protein, and these are the lipid molecules. As I know that, as we discussed, that it's sort of a transmembrane, we can say. Okay, this entire membrane is incorporated well within this bilayer membrane, and within this entire membrane protein, what I am concentrating is that central portion. That is what I am going to study extensively in this particular. That are the blown up picture here. It shows that whatever the balls, red balls, you see that is the one what we are interested here. Okay, basically this rhodopsin can be represented in this particular fashion. Okay, this is the molecular structure of that particular rhodopsin. Okay, it has several methyl groups. Okay, instead of methylene groups, we are considering couple of methyl groups, which is located at 5th position, 9th position, and 13th position. And what we do is, whenever we want to study dynamics or any of the studies associated with this kind of a membrane protein, we select two methyl groups, and selectively we deuterate, we replace hydrogen with deuteriums, hydrogen with deuterium independently, and then we make the measurements. And whenever we have to make this measurement, it is not an easy job. Okay, as you know that they are all light, in the sense the property of the material would change as soon as light falls on the given material. Okay, there will be resistance, conformational change happens whenever light falls on that. I am not spending much time on this, just to give you that how one can extract very good information from these type of studies. Okay, and here what I am doing in this particular case is I am replacing hydrogen selectively, hydrogen with deuterium, and I will perform deuterium NMR relaxation studies. Okay, whenever I do relaxation studies, as you can see that this particular spectrum, okay, it goes from negative maximum intensity to positive maximum intensity. Okay, and from that I can calculate what would be the relaxation time for the methyl group, which is located at C9, and what is the relaxation time at which C13 methyl group is relaxing back. Okay, this is basically CH3 group. You know that threefold rotation, it can happen. Okay, and one can estimate by measuring this relaxation time as a function of temperature. Okay, one can estimate how much energy is required for that methyl group to reorient from one equivalent position to another equivalent position. That we call it as activation energy. Okay, what is the activation energy required for the molecule to undergo motion? That can be studied using this kind of deuterium NMR spectrum. Okay, and once we know that, okay, by making several measurements as a function of what I do, I measure the relaxation time as a function of temperature, and then I will plot it ln of T1Z as a function of 1000 by T. Then I get this kind of a graph. And what is the particular temperature at which I got minimum relaxation time? Okay, that would help us. This is basically 1 over T1 if I consider maximum relaxation rate or minimum relaxation time. Okay, that would help me. Okay, that would happen whenever the motions, okay, assume that this is the particular temperature at which I got the minimum relaxation time. That would help me to estimate what is the corresponding spectral density associated with that. Okay, that would help us to estimate what is the energy required for the molecule, okay, to reorient. And that type of relaxation rate data is extremely essential for molecular dynamics simulations. Okay, and hence In that way, this data is extremely useful in our drug industry. Okay, I am not spending much time over that. My interest was only to give you for what type of biological systems NMR
Sir,
can be applied. Yes,
I have a question.
yes, please.
I mean, it's a little away from the topic, but the question
Yes.
is like, suppose I have a compound which shows the adsorption of water, H2, okay, and D2 also. So can I take the 2H NMR of that compound?
1 minute, please. Can you please repeat your question?
My compound shows a reversible adsorption and desorption. That means
Uh-huh.
sorption of water as well as D2.
Okay.
So what changes can I expect from the 2H NMR spectrum?
Adsorption and desorption study, I have to think about it, because whenever there is a change in absorption, okay, how many water molecules are trapped in your given system? Okay, what is getting adsorbed in your system?
Water, H2 and
Yeah.
D2. H2 and D2 selectively.
Yeah, then one can always measure the concentration of water present in the given material. Okay, that gives the intensity of the NMR signal. Okay, we have to read certain literature associated with that. Okay, but in principle, that should be possible to measure. But exactly how do you know that whenever adsorption has happened, you have to keep your entire sample in the same state, okay, till you complete your NMR measurement. Or you have to do in situ measurement of adsorption when you keep your sample inside the magnetic coil, and then your adsorption should happen. Then that is one way. Okay, or we can always have a private chart associated with that one, because unless I go through some of the literature where they have done it, okay, I cannot make any concrete statement.
Okay.
Okay, because we have to read that. That seems possible, but please, I'll come back to that point where we have limitations. Okay, then you will realize that what would be the problem, or how, where else you can go and get that work done. Okay, whether it is possible in the available equipment with you or not. Okay, can we move ahead?
Yes, sir. Yes.
Okay. Now, once we know that we can measure relaxation time, and then from that I can get the spectral density, then I will be knowing what type of motion is happening in the biological system. Now we will switch over to inorganic system, okay, or metal halides. Okay, some of the samples or whatever the systems I worked on, that I have taken it. Okay, let us try to understand. Let us take two types of systems. One is trimethyl ammonium trichlorogermanate. Okay, other one is tetramethyl ammonium hexachlorophosphate. Okay, let us consider what are the things one can expect. As it is shown at the top, okay, I can measure solid state NMR. Okay, through solid state NMR, I can measure 1 minute. Okay, through solid state NMR, one can measure valuable information that is related to molecular structure and dynamics associated with that, and what type of phase transition, or whether any phase transition is happening in the system, can be measured using the solid state NMR. And I can also, whatever the relaxation rate measurements I do it for the inorganic system, that can be correlated with the conductivity mechanism happening in the system. Okay, all these things can be correlated along with optical measurements and electrical measurements also. Okay, all things are possible. Just to give you little information about how one can measure those kinds of parameters through NMR. Okay, let us take these two examples. Okay, first one is trimethyl ammonium trichlorogermanate. Okay, through which I can identify the phase transition, and also I can measure the quantum rotational tunneling happening in the system. Let us see what we do. Okay. Whenever what I do, in the sense, this is my thesis work, what I did 10 years ago. Okay. More than 10 years, 10, 15 years ago. That time, what we measured is, we measured spin lattice relaxation time as a function of temperature. Okay. And this compound was prepared. Okay. Routine, XRD, and other characterization were done. And then we measured this relaxation times as a function of temperature. Okay. And please remember, look at this. The bottom scale shows that 1000 by T, and top scale shows that the temperature goes down to 10 Kelvin. If I want to make any measurements up to 10 Kelvin, what I need? What do I need whenever I perform the experiment? How can I reduce the temperature? Yes, guys, any clue? Can I reduce the temperature up to 10 Kelvin in a normal case? Okay.
Nitrogen gas.
Yes, nitrogen. What is the minimum temperature I can go with nitrogen? Yes, it's a good answer. You know, as a typical teacher, he won't stop.
I mean, nitrogen gas, I can 80 Kelvin, 100 Kelvin. Does it go below that?
No, usually nitrogen, liquid nitrogen goes down to 77 Kelvin is its boiling point, boiling temperature. Okay. Whenever I have to go below 77 Kelvin, I have to go with liquid helium. Okay. And whenever I perform this experiment, I have to make sure that my entire sample is at that particular temperature. Hence, we need a indigenous experimental setup. Okay. And commercial spectrometers, most of them, they can go below about 10 degree or 20, 30 degree max. Okay. Only few spectrometers or facilities, they would allow you to do experiments up to liquid nitrogen. It is extremely difficult to do NMR measurements at very low temperatures with your conventional facilities or centers. Wherever you submit the sample, they will do experiments for you and do it. Hence, to do these kinds of work, we had to design our own NMR spectrometer. Okay, and hence we constructed our own NMR spectrometer and we perform these type of measurements indigenously. Okay, we'll talk about that in a while. Okay, what do you
Sir,
get?
excuse me, sir. Using helium, will it make this expensive?
Yes, of course.
And can dry ice also be used?
See,
Or
dry ice can go up to probably minus 20 or minus 30 degrees centigrade. That I can say that 250 or 273 is our 0 degree, right? Is it right? 270 Kelvin, 273 Kelvin is 0 degrees.
Hardly it goes till 250 Kelvin. The dry ice.
How much?
250.
Yeah, 250. That's what. Another minus 10 or 20 or some sort of salt mixture can go little below that. Okay, not much of that. Okay, and also it is not only keeping that. You please remember, you cannot keep entire the dry ice within that NMR coil. Do you remember? That's why I showed you the picture of the NMR coil that will be having about 10 mm dia, 10 millimeter or maximum 5 millimeter diameter. Where do you keep your dry ice? Hence, I need a cryostat. Those experimental details, because I had built my own NMR spectrometer for my thesis work, I did not include here since it is for the biologist. Okay, experimental, I don't want to scare you with the experimental details, but to do these kinds of particular experiments, we need our own equipment, or we need to work little more to extract this kind of information. But once I get this kind of information, it is easy to analyze the data and easy to publish it also. As I told you in the beginning, either I do complex experiment and my analysis will be easy, or I'll go with simple experiment. I just submit the sample, prepare the compound, submit the sample, he will give the spectra. Then I have to break my head to analyze it so that it will be published in a very good journal. Okay, both are quite possible and both are equally good, but we took a different route throughout our research journey. Okay, for that we had to use helium cryostat, and continuously helium, liquid helium was pumped into the entire sample chamber. Okay, you can watch my YouTube video where I have talked about that cryostat structure. Okay, how do we do this exact measurements? Okay, for us right now, what is important is that what type of information one can get from these kinds of NMR, solid state NMR. That's my intention or scope of this particular talk. Okay, as you can see that this relaxation time is not always constant. It keeps coming down during whenever the relaxation time is decreasing. As I decrease the temperature, see here, this is 1000 by T. If number is more means low temperature. Okay, number is high means 1 hour 30. Okay, 300 is approximately 3. This is my room temperature reason. Okay, then what happened? This relaxation time came down, and it reached the minimum value. If I measure it, all these, that entire NMR data was collected at 20.53 megahertz. You might be laughing at me. Okay, all of you would have done it, or most of the experts, they talk about 200 megahertz, 500 megahertz, 600 megahertz. Okay, that is the operating frequency of their spectrometers. But for us, whenever I want to study slow motion, as I mentioned it earlier, depending on the motion I want to explore, my operating frequency should match to that. Okay, if not, if I am not able to match it, then again I can decrease the temperature so that motion becomes slower at that particular temperature. I can measure what type of motion is happening over there. Okay, for that, here, as you can see that the motion will be in the order of 20 megahertz at this particular temperature. Okay, then I can identify what type of motion is happening in the given material. Okay, what is the speed at which your molecule methyl group, as you know that this is trimethyl ammonium trichlorogermanate. Okay, we have a methyl group, CH3 group. How well it goes from one equivalent configuration to another equivalent configuration, what is the energy required can be measured, and those energy values are given as 4.4 kilojoule per mole, 20 kilojoule per mole, 27.9 kilojoule per mole in different sectors. Okay, as in principle, what we were expecting, there was a straight, there should have been a straight line. It should have decreased drastically. But in our system, it did not happen. And when we estimated activation energy, this is supposed to be only one activation energy I was supposed to get it. But we were getting different variation in the relaxation rate as a function of temperature. It's provoked us to do differential scanning calorimetry measurements. Then we saw that several peaks. Okay, those who are physicists, do you know that where do we use this differential scanning calorimetry? Okay, and this differential scanning calorimetry gives us what are the phase transitions happening in the given material. And at the same temperature in our NMR data also, we were seeing this slope change of this set of data with respect to this set of data. Again, this set of data with respect to this set of data. Hence, by measuring the solid state NMR also, I can identify the phase transition temperature, but I may not be able to exactly say what type of phase transition is happening. Is it the first order phase transition, second order phase transition? That we may not be able to do it explicitly with NMR, but I can identify the phase transition temperature. That can be correlated with the
Sorry to interrupt. So it's very wonderful. I mean, this is really wonderful. I have a question. The
Yes.
question is that, yeah, I do DSC, single crystal XRD and PXRD. So basically, when we have to talk about the phase transition, we take single crystal XRD at different temperature. So the phase that I'm talking about is the space group. Like suppose it was P2121 space group, it is changing into P1 bar or PNA21. So this is what I mean by phase transition. So this is what you are also talking about.
Yes. That's right, but only let me clarify at this point before you continue with the next part of the question. I cannot identify from what phase to what phase it is going from this type of measurement alone. Okay, I cannot only phase transition is happening, I can identify from this measurement, not the exact phase group.
Yeah, I mean,
Yeah, I
it's
hope
happening that we can
that's,
tell.
yeah, please continue.
Yeah, I get it, sir. That was only my question.
Yeah, that's fine. That exact one, we don't measure it here. Okay, that is not possible with this itself. Okay, for that, we will try to understand at the later part what else can be done. Okay, and that is with respect to one system.
So one more question from the
Yes.
last slide. This trend of this energy. Suppose this is at 323 Kelvin, it was 4.47. Then at 270, it is 20.53. Then 27.90. It
Yes.
is increasing. So what do you say from there?
Yeah, here it totally tells that at higher temperature, it follows a sort of simple cubic system where whenever we are having a simple cubic system, it doesn't require higher energy for molecule to reorient. Okay, the system is very simple system, but as we decrease the temperature of the system, it gets into that could be some other complex what we can say that crystal system. Okay, what I can say that is the molecule is undergoing a phase transition, but it is going from simple cubic system to some other system. Okay, that explicit measurement with XRD and other things we can make it if we have a facility to measure XRD as a function of temperature down to these lower temperatures also. Then I can correlate, I can tell that at higher temperature, it forms, actually we predicted at that point, it was in 2007 when we published it. Okay, we predicted that that is almost equivalent to, for a simple cubic system, this much energy is expected for this kind of a complex system. Okay, and please remember, whenever we study, we can study two types of motion. One is CH3 group itself, another one is NCH3 thrice. Okay, one is methyl group and also trimethyl group. Together we can study. In principle, we were expecting two minima, one corresponding to methyl group alone, other corresponding to methyl along with NCH3 ammonium molecule you have taken, right? Basically, it is ammonium chloride where every H is getting replaced with CH3 groups. Okay, two types of motions one can expect. Okay, since in our system, they are almost merged together, we got only one minima. That's why this activation energy is attributed to. In the later stage, I will explain, or I do not have complete details here. I have not shown it intentionally. I can distinguish how much energy is required for methyl group, how much energy is required for NHCH3 trimethyl group also. One can estimate. Okay, can I move ahead?
Yes, sir, definitely.
Okay. Now another system is this tetramethylammonium hexafluorophosphate. As you can see that this is an interesting compound. Okay, I have different NMR active nuclei here. Okay, for in principle all are NMR active nuclei except this nitrogen. By default, NMR nitrogen 14 would become NMR inactive. Whenever I replace with N15, I can do for nitrogen also, I can do NMR. I can do NMR of carbon. I can do NMR of proton, that is hydrogen. I can do NMR of phosphor as well as NMR of fluorine. Okay, what we did in this particular sample is that we collected the data for phosphorus 31 and we performed this NMR of two nuclei, fluorine as well as hydrogen, as a function of frequency also. If you would have looked at complex mathematical expression, I wrote it earlier. Okay, your relaxation rate does depend on frequency, okay, as well as the temperature. Okay, one can measure relaxation rate as a function of frequency, that we call it as fast field cycling NMR experiments. Okay, it is not so familiar with among chemists. Okay, but nowadays there are ready equipments are available where I can feed from what frequency to what frequency relaxation I want to measure it. Okay, there are equipments, fast field cycling equipment. Then I can do complete measurements. But what we did at that point is we measured for fluorine as well as hydrogen independently. For hydrogen, I made this measurement at 3 frequencies. As you can see that this is the magenta color triangles, open circles, and square filled circles, filled squares. All of them are for proton NMR. As you can see that the proton NMR at high frequency, they really, what frequency you are making measurements, they do not matter. What matters is below this or below this temperature, wherever we get this minimum, okay, from that point onwards only, it depends on the behavior, depends on what frequency I made this measurement. Okay, and from all these things I can estimate what is the activation energy corresponding to the motion associated with a functional group which has hydrogen. In this case, the functional group is CH3. Okay, CH3 motion's activation energy can be measured from this slope of this curve. Okay, in the similar way, whenever it comes to lower temperature, okay, I can, that is for the hydrogen. Now let us consider this PF6. Okay, what we consider CH3, this tetramethyl ammonium group, we call it as cation. Okay, PF6 is anion. PF6 also, P is surrounded by 6 fluorine atoms. It also undergoes motions. That PF motion can be measured, and the energy required for this PF motion can also be estimated by making this type of measurements. As you can see that for the fluorine nuclei, we did it at 21.34 megahertz and 16.10 megahertz again. Okay, and we got this scattered data. As you can see that within the all my relaxation measurements, whatever we have shown, the error bar is well within the dimension of the symbol shown here. And the variation here, whenever PF anion motion is happening, okay, at the same point, whenever the maximum relaxation is happening for CH3 also, I can see the variation. Can you see that wherever the minimum is observed for the proton signal or proton relaxation time, I can see little variation from the fluorine NMR relaxation rate also. All these things would help us to understand what type of cross relaxation is happening between fluorine and hydrogen. Okay, same thing is applicable for the phosphorus also. PF and PF motion associated with, in the sense, can be studied with phosphorus NMR as well as fluorine NMR. As you can see that whenever this motion is happening, here also I see similar variation over there. Therefore, one motion influences the other motion. And all these things are very much useful for potential technological applications. Okay. Any doubts in this particular case? Okay, just to extend this portion, whenever we try to understand, this is this slide talks about that the finer details associated with this kind of motion. Okay, one can estimate or one can write the mathematical expression associated with this fluorine relaxation time as well as proton relaxation time. That would include lot of complex motions associated with our cross relaxation terms associated with hydrogen and fluorine, independent fluorine. Okay, and there are some more concepts. We are not, this is beyond the scope of this talk. That's why I'm not talking much about the variation or the data analysis associated with that. As I told you that if I want to fit this kind of complex equation, I can go with any of our standard software like Origin, MATLAB. I can write the code myself and fit the data and get the measurable parameters from this. Okay. And
Sir, one doubt I have small.
yes,
Suppose you have more than one type of hydrogens present in your lattice. Like you have a CH3 group and you have an NH2 group also.
Ah.
So can you go to the back slide? The back slide?
yes.
Yeah. So here, if you're talking about this this time temperature dependent thing for the CH3 specifically, so is
Okay.
there a standard data table where we come to know that which one is for which hydrogen?
No, here that's where we are considering here all CH3 are equivalent sites, right? Here. Can you see that? The CH3
Yeah,
group.
here it is equivalent. But suppose I have an NH3 group along with this. So how will I come
Yes.
to know?
That's where that time we have to selectively deuterate one of them. Okay, we can always do selective deuteration. One of them we have to discard it. We from this low resolution NMR spectrometer. That's what. What do you mean by low resolution NMR spectrometer? Is where I do not. Please remember, all these measurements are done using oscilloscope. Okay, I never recorded NMR spectra throughout whatever I am talking for the inorganic material. I never recorded, and for my entire research work over last 20 years, I never interpreted my NMR data in terms of chemical shift. Okay, this was done with dedicated equipment, time domain measurements we do. First, we record the NMR signal. Okay, we measure the variation in the intense magnetization as a function of that tau, what I showed in the beginning. From that, I estimate the relaxation time. Okay, these are all time domain measurements. What I am driving at this point is that if you have CH3 group and plus NH3 group, okay, if you go and if you submit your sample to the central facility, where it would give 2 NMR peaks, right? When you do the Fourier transform of that, is it not? Can you identify 2 different peaks for
Yes,
CH3
yes.
group and NH3
Yes.
group?
Yes, definitely.
Then, if that equipment has temperature variation facility, then you can perform this experiment. That's what on our rhodopsin sample I showed, na? Where we get at the same time, I can get different peaks for different positions of the lipid molecule. I can estimate relaxation time for different methylene groups present in the same compound. Like that, you can do. Only thing is whether that facility where you are submitting, whether they have option to change the temperature down to this liquid nitrogen or liquid helium temperature is our task. What we need to explore first. Okay, that's why most of the people, they stop doing measurements around this liquid nitrogen temperature. They do not go for liquid helium temperature because, as you know, that the cost of the spectrometer is very high and they cannot invest their entire time and money, okay, for making this type of measurement explicitly. Okay, where this is that's where that was the need for me to design NMR spectrometer on myself or our lab members. You can try up to nitrogen temperature or close to that. There are certain specialized facilities, they do make measurements as a function of temperature. And also,
Just one last question, and I'll not ask any question. Where in India can we do these kind of measurements?
these measurements, one is our research group, they do. Okay, just to give you a hope on this, is that if I want to measure the relaxation rate, to measure the activation energy associated with the molecule, I need only this left-hand side data points. Assume that this is, I started with 400 Kelvin, okay, and I stopped at 300 Kelvin. Okay, this much data is sufficient to estimate activation energy. Okay, rest of the things from this data, I can always extrapolate and get this minimum. Okay, I don't need this entire data if my job is only to estimate activation energy associated with that. Okay, because I wanted to explore some more things, some more type of motions associated with that, like quantum rotational tunneling. As I told you that, I hope I have heard about this quantum rotational tunneling. Anyone? It is something like that. Tunneling is whenever a molecule cannot go from one configuration to other configuration, it has to overcome the potential barrier. Okay, what would happen in quantum rotational tunneling? If energy is not sufficient to go from one equivalent position to other equivalent, or if the supplied energy, thermal energy is not sufficient to overcome the barrier, it can penetrate through that. That we call it as quantum rotational tunneling. Whether that is happening in the given system can be studied in this particular measurement. Okay, for that purpose, we intentionally did these type of specialized measurements. Okay, is it okay? And now, as you, by fitting your experimental data with this complex equation, I can estimate what would be the percentage of hydrogen bonding present. Okay, what type of interaction might be happening with the PF6 system and trimethyl or tetramethyl ammonium molecules. One can estimate out of that. Okay, and the last one is when this is for a hardcore physics students, I can study these magnetic samples using this NMR. All of us know that what are ferromagnetic system, antiferromagnetic system, and ferrimagnetic system or paramagnetic system. Okay, these type of materials can also be studied using this NMR. Okay, to do that, that kind of measurement we call it as zero field or internal field NMR. For those kinds of magnetic systems, I do not have to pay for external magnetic field. All of you know that those superconducting magnets, if they have to operate, I have to keep on pouring liquid helium. I have to keep on pouring liquid nitrogen on a weekly basis as well as monthly basis. That's why maintaining a dedicated NMR spectrometer is extremely expensive. That's why only central facilities or major ones, major labs would be having those spectrometers. Instead, in the zero field NMR, I don't need any external magnet. And another one is for in conventional NMR spectrometer, okay, can be for conventional NMR can be performed for all NMR nuclei. But for zero field NMR, my sample should be ferromagnetic or antiferromagnetic or ferrimagnetic samples. And my NMR frequency, the operating frequency of the spectrometer is directly proportional to the strength of the external magnetic field where I am keeping my sample. Okay, but for zero field NMR spectrometer, it purely depends on what is the internal magnetic field present for your sample. That is, internal magnetic field present in your sample decides the operating frequency. Now, the complexity comes into picture. When we are having, we know that 500 megahertz means I know what is the, whatever the sample you take, I will record NMR signal at 500 megahertz. Okay, but here, whatever the sample I take, I have to change my entire hardware to tune to that particular frequency. Then only I will make zero field NMR spectrum. Or if I want to record zero field NMR spectra, then I have to tune my entire electronics to tune to that frequency so that I will be able to make the measurement. It purely depends on what is the magnetic field strength possessed by these ferromagnetic materials. Example, as far as examples are concerned here, the general molecules or nuclei measured over there: hydrogen, deuterium, fluorine, carbon-13, and nitrogen 15 and phosphorus. These are all conventionally measured in any of the equipment. Okay, in zero field NMR, mostly we go with iron, cobalt, or nickel, or manganese. Okay. In both the cases, the operating frequency does depend on what is the magneto-gyric ratio gamma here. Here also magneto-gyric ratio plays important role corresponding to the operating frequency. All of you would have, if any of you have recorded NMR spectrum, okay, for 500 megahertz spectrum, whenever you, when 500 megahertz spectrometer, when you record the NMR spectra for hydrogen, it will be 500 megahertz. If you go to carbon, what would be the frequency at which you are making measurements? Yes, anybody has done carbon NMR? Recorded? It is much smaller operating frequency, but still the equipment is called as 500 megahertz spectrometer. I recorded the spectrum. When you record it, you don't explicitly mention that what would be the frequency. Again, when you go to any 300 megahertz, a 300 megahertz NMR spectrometer, if I want to study deuterium NMR, then my gamma value for deuterium is much smaller than that of the hydrogen. Then my operating frequency comes down to 46 megahertz. Okay, it is much lesser value than that of the hydrogen. Similarly, I will be having different operating frequency for carbon or any X nuclei, they call it. Okay, but here when I am talking about zero field NMR, I have to fine tune my spectrometer to make it to work in that particular frequency. Okay, now it is, if not much physicists are there, I will try to skip this. Okay, along with that, whenever the effective field seen by the nucleus depends on what is the field, what is the external magnetic field, if at all, if I am applying, and what is the dipolar field associated with that, and what is the hyperfine field associated with that. This is the complete field, effective field seen by the mass. In ferromagnetic materials, the internal field generated due to magnetization, because of the different origins. Okay, and that is sufficient for us to make NMR measurements. I don't need external magnetic field. The meaning of this entire sentence is that for ferromagnetic materials, the internal different magnetization mechanisms, they are sufficient enough to create whatever the magnetic field required to make one energy level into two energy levels. That's why I don't require external magnetic field. And this dipolar component is due to the combined fields of different electronic moments also. Let us not really spend much time on that. Okay, what you have to understand here is for ferromagnetic systems, okay, I don't need to apply external magnetic field. Okay, as you can see from this from this slide, for ferromagnetic system, for example, I have a cobalt or nickel or iron. Okay, I can estimate what would be the magnetic field seen at the site of the nucleus. For cobalt system, the strength of the hyperfine field seen at the site of the nucleus is close to 21 Tesla. Okay, please remember 100 megahertz spectrometer, okay, or 42 megahertz for the proton corresponding to 1 Tesla. Now, my cobalt system, without applying external magnetic field, okay, at the site of the nucleus of the cobalt, I can see about 21 Tesla magnetic field. And if I substitute corresponding gyromagnetic ratio for the cobalt, okay, then I can get an NMR or expected resonance frequency will be in the range of 220 megahertz. Okay, whenever I do electronics which can detect NMR signal at 220 megahertz, okay, I can detect the NMR signal. Okay, this is estimated value. In the realistic case, one can observe NMR signal which could spread from 200 to 230 megahertz for the cobalt system independently. In the similar system, or similarly, if I take any compound which is having nickel as a system, nickel is present in that, then its hyperfine field is 6.5 Tesla, depending on its gyromagnetic ratio gamma. Okay, the frequency will be in the range 26 to 28 megahertz. And if we consider any iron system, pure Fe system, the hyperfine field will be in the range of 45 to 47 megahertz. Okay, whenever we have alloys which has both iron and cobalt, again the frequency would go from 200 to 300 megahertz, depends on what is the prominent nuclei present in your alloys. Okay, some of instance, one of my PhD student is working on these kinds of alloy systems right now. Okay, whenever, as you can see that now I have to design my own spectrometer. With that spectrometer should be capable enough to tune to any of these frequencies. Whenever one person gives signal sample which is containing nickel, then I have to make sure that my spectrometer works in this 26 to 28 megahertz, otherwise about 50 megahertz or 200 megahertz. Hence, it is, if I want to do that, any of the central facilities may not entertain us to do such kinds of experiments. Hence, we need to have our own design spectrometer. Okay, let us, in the similar case for manganites, then operating frequency goes up to 700 megahertz from 300 megahertz. Then I need to work more on that. Okay, now, as I already explained that I cannot go to any central facility, go do the NMR, record NMR spectrum for me. Okay, I cannot go with these kinds of ferromagnetic systems. For that, I need to design my own NMR spectrometer. Hence, in our labs, we build our own NMR spectrometer. It is not that much hard to build it. Okay, what we do is, okay, we take one signal generator and we take our pulse generator, and pulse and RF signal is mixed together, and then we use an amplifier and we send that mixed RF to the sample coil where I keep my sample. This is true. This is the same block diagram used in our conventional commercial spectrometers also. Okay, but here why we have to do it ourselves, as I explained earlier. If I want to change the operating frequency, then the signal generator should be, I should be able to change the operating frequency corresponding to my system. Hence, we try to do, then rest of the electronics also, this transcoupler, I have to change it depending on the operating frequency. Hence, it is more desired to have our own dedicated NMR spectrometer. As I told you, again, I am repeating again and again, whenever we have our own equipment, whatever the time it consumes, we don't have to pay for it. Okay, it is sort of a one-time investment of our time. One lab member, if they create NMR spectrometer, then we can start continuing using the same equipment with little modification from one system to other. And here, same, the logic remains same. Your sample is kept outside because of the external magnetic field. Two energy levels have already been formed. At that point, I will send radio frequency pulse to that. Whenever it matches with the energy gap between these two energy levels, then transition happens. NMR signal appears that will be picked up by the receiver amplifier, and then I connected. The receiver is connected to my PC. Then I will get the NMR signal. Okay, this is the bottom line of this is to do some special measurements. We need to have our own dedicated equipments. Okay, that's why our students spend much of their time to have these kinds of equipments. And whenever we have, okay, this is one of the samples what we work. Okay, nickel ferrates, they are basically inverse spinel, they follow inverse spinel structure. And this iron, whatever the iron we are considering, okay, some of these irons could go and sit at two different sites. Okay, one site, A site, whenever we talk, it follows this tetrahedral site. As you can see that your iron is at this point and other four oxygens are connected in this way. In a similar fashion, okay, some half of the iron atoms follow or sit in this tetrahedral site, and another 50% of the iron atoms would go and sit in octahedral site. Okay, here octahedral site, as you can see that your material, okay, your atom, that is red colored iron is surrounded by 3 neighboring or 6 neighboring oxygen atoms. That follows octahedral site. Okay. And whenever I want to measure, okay, where exactly my iron is going, in the sense what I have shown here is these are the two possibilities. If I consider only pure nickel ferrite, 50% would 50% of the iron would occupy octahedral site, that is B site, and 50% of them would go for tetrahedral site, A site. Okay, but these kinds of materials, whenever we want to study, okay, I can study that. But if I change some of the compositions here, if I change the composition of iron, for example, as you can see that whenever I change the composition, or if I keep substituting aluminum in place of iron, then if I want to measure where exactly which type of iron atoms I am changing, whether iron present following the tetrahedral site is changing, I am changing with the aluminum, or iron situated in the octahedral site, those irons I am replacing with aluminum. If I want to study simple VSM measurements or magnetization measurements, where conventional facility where I can supply the equipment, I can give my prepared sample and ask them to record this VSM measurement, that would not or that won't help completely whether my iron is or aluminum is going and sitting replacing tetrahedral sites of the iron or octahedral sites of the iron. I cannot detect it. That is microscopic magnetization variation, or the cation distribution happening in the given system cannot be measured accurately with this type of conventional technique. For that kind of system, I need to rely on internal field NMR. Okay, what internal field NMR tells here is, whenever I record iron NMR, okay, 57 iron NMR, then if I vary the operating frequency of my spectrometer, I will get signal, that signal strength at 68 megahertz. It doesn't show anything. After that, if I keep on increasing and it follows through a maximum value, and again it comes back, and at the lower end again it goes up and comes back. And these two peaks, whatever conventionally you saw it as a single two peaks, okay, the low frequency peak is corresponding to B sites, okay, and the high frequency peak corresponding to A site. Okay, I can distinguish where exactly my iron is going and sitting here. Okay, this is for the pure system. As you can see, go to the bottommost line. Okay, when I have increased, okay, this is a different example. What I am doing it over here is, what I am showing it here is, it is not aluminum I am changing it. Okay, here I am changing at the iron site, I am changing the cadmium. Okay, when I change the cadmium concentration from 0 to 0.4, okay, then I did not see any peak corresponding to my A site. That clearly shows that, okay, M ions occupy octahedral B sites and iron ions distributed between A and B sites. Ultimately, I have replaced all the iron atoms which were located in A site, or have got shifted to B site. And with a little more detailed analysis with other conventional spectroscopic techniques also, we were able to exactly measure what is the percentage of ions got distributed among these two sites, and as a function of addition of cadmium ions, how well cation redistribution has happened quantitatively one can measure. Okay, that work was done here. Okay, and that was very well reported, and that kind of microscopic information, it is hard to get it from other technique except mass bar technique. Also, we can get similar type of information. Okay, what we are trying to focus or show here is our internal field NMR is much analogous to your mass bar spectrometer also. That kind of studies can be done in terms of inorganic system. Okay, it would help us to make even the phase confirmation, what you are asking initially, that kind of whenever we are having mixed phases, that can also be measured using internal field NMR. Okay, and here there is a lot more finer details. Okay, since we are having less time, I will not get into finer details of this. Okay, how really happening. Okay, how domains and domain walls would enhance the radio frequency RF field whenever we shine radio frequency signal. Okay, from the signal generator, how enhancement happens, how one can measure it, can be discussed, or all these details are discussed in our publications. You can go through it, and if you have any questions, you can come back. And another one, what I need to highlight here is, whenever, for example, you assume that you synthesize a compound, okay, that compound has two phases. Okay, one is, for example, cobalt. Okay, when we synthesize this cobalt, okay, cobalt synthesizes both in FCC and HCP phase. Now, for that HCP, okay, whenever I perform the NMR measurement, I will get independent peak at 21.13 Tesla for whenever cobalt follows the FCC structure. Whenever cobalt follows the HCP structure, the internal field would increase to 21.87 Tesla. If I convert this magnetic field in terms of NMR frequency, I can see there is about 7.4 megahertz difference between two peaks what we observe in this NMR, internal field NMR spectra. Hence, it is easily distinguishable by IFNMR. Okay, and then low frequency signal is whenever we see two signals, I can always attribute those signals to FCC phase and HCP phase. And once I know that, I can always estimate domain wall contribution and domain contribution. For that, okay, these details I will skip it. What I need to show here is the bottom line of these kinds of discussions. Okay, for example, you prepared your own cobalt. Okay, and now your new, whatever the compound you have prepared, it has both phases, FCC and HCP phase. Unfortunately, as you can see that from ICSD data, there are three peaks. Okay, it is around 44 2 theta angle, 44 degree and 75 degree. Okay, I have two peaks at the same position for both FCC phase as well as HCP phase. HCP phase and FCC phase. I have peaks corresponding to both the phases. Hence, whenever you record your news, whenever you record the XRD of your own sample, I will get two peaks. Same, how do you really quantitatively tell that that is due to FCC phase or HCP phase? It is extremely difficult to distinguish whenever we have mixed phases like this, as predicted here. Okay, for that we prepared cobalt using different wet chemical synthesis methods. One, we purchased it commercially available cobalt, and we prepared another cobalt as water as a solvent, and the third system is ethanol as a solvent. We prepared it and we recorded the XRD, and also we recorded the SEM images. As you can see that whenever we have that ethanol was used as a solvent, we got dendrite type structure, and whenever we used water as a solvent, it was trying to give spherical images, and commercial sample, it is already well-known fact. Okay, we got this kind of morphology, but we can clearly see that morphology is different from XRD. I am not able to distinguish which phase is dominating when what type of solvent was utilized or used. Okay, for that we did NMR of these three samples. Okay, you can clearly see that Okay, commercial sample gives these two peaks, and we can interpret the variation in the line shape with the different, what is the effect of grain boundary, what is whether FCC, what is the contribution from the FCC, what is the contribution from the HCP phase. Okay, I can distinguish how whenever I use water, okay, we got the mixture phase, okay, mixed phase, FCC and HCP, both phases were consecutively present, and when the commercial sample was completely FCC phase, whenever we changed water to ethanol, we got most likely towards the HCP phase, because my signal is appearing at the higher frequency, and commercial compound was giving signal intensity was concentrating more towards the lower frequency. When I used water, then I had both equivalent distribution approximately to both high frequency as well as low frequency. Hence, through this quantitative analysis, as you can see that fitting is done, calculated area under each component, okay, we were able to estimate what is the percentage of phase component present. Okay, that is the advantage of these kinds of internal field NMR spectroscopy. Okay, hence these are the finer details what I talked about it so far. Okay, like this, quantitatively I can measure it based on the area. I can estimate what is the major composition present when different type of liquids or solvents were used. Okay, this is extension of that work, and I'm not going to talk much at this point. This is the same slide what I showed in the beginning, that cadmium concentration variation. This graph you know already. Okay, probably at this point I will stop my. These are all just to give you a hint that, okay, one of our recent paper, we connected 3 different techniques with our internal field NMR from Raman studies and XRD techniques. We calculated what is the amount of iron present at octahedral site and what is the amount of iron present at tetrahedral site also. And we got wonderful correlation from all 3 techniques. Okay. From that, the cation distribution, whenever we want to study for domestic applications or any high frequency applications, these kinds of alloys or ceramics are extremely useful. Okay, for transformer applications, wherever high frequency applications, okay, they are highly magnetic but less electrically conductive. Okay, that kind of applications where we need to reduce the eddy current produced in that. Okay, we go with that. We use these kinds of materials to know that why they behave like that exactly. Okay, these type of different techniques can be correlated together to understand the mechanism happening in the given system. This is our recent publication in the last year. We can go through it, and if you have any doubts, you can always come back and talk to us, so that what we understood so far, this is the biophysical conclusions. Yesterday's class, okay, we talked about different motions or different forces happening in the biological systems. One, we could measure it, and from our inorganic materials, we were able to measure what are identify phase transitions, and also quantum rotational tunneling frequencies. We were able to measure it. From zero field NMR, we could able to measure many. We could able to compare different techniques, and also we were able to measure cationic distribution happening in the system, and also phase confirmation, which is hard to quantify with other techniques, that can be done using this zero field NMR technique. Okay, with that, I have to thank many people in this particular case. Okay, one of the examples, if I have to consider at this point here, is that, okay, the organizers, Sabir, I have to thank him, and also I have to thank my financial support what I received from our Gokula Education Foundation, and I should most of the work biological system I did it at University of Arizona in collaboration with Indiana University and Purdue University. Okay, this is the cactus symbol of Arizona because it's a desert, as you can see. Okay, and as yesterday they introduced, okay, I graduated from Bangalore University. It greatly helped me in framing my career, and of course I worked and as a student and as a faculty at Indian Institute of Science. Okay, that all most of our NMR work, low temperature work, was done at NMR Indian Institute of Science. Okay, and also most of the inorganic materials work is published in this particular textbook. It is available in Amazon or any other site. Okay, you can go through it. Okay, now I am thank you for your patient listening to me. Okay, once again, thank you to everyone. I am ready for questions.
Thank you so much, sir. It was one of the best lecture I heard. So participants, if you have any queries, you can unmute yourself and ask. And sir, there are a couple of questions in the chat box. I think you can access it.
Can you please narrate me if you are able to, because I don't know where else I need to go and check.
It's okay. It's okay. I can. In fact, the questions were asked in between, not now. So you may have to recall the things. So the first question from Ashok Kumar sir: how can we selectively exchanging D2 with H?
How can we
Selectively exchange D2 with hydrogen?
If that person is still online, okay, can you please narrate your question?
Sir, this is how can you exchange selectively deuterium, hydrogen with deuterium?
See, what we did over there is, okay, that was done. We collaborated. Okay, if you are talking about the membrane protein that rhodopsin, as an example, okay, we collaborated with our Japanese group, and they did it for us whenever we go for selective replacement. Okay, we did not do it in our lab. Once upon a time, our lab did that, in the sense US lab, they did it. Okay, after that, we simply, what we can say, outsourced our research problem to them. And they were doing it. But once we get back our protein, then embedding that protein into the membrane system, work was done at our end. Okay, and they also do not disclose some of the finer details with us. Okay, because that's an established group. That's why I am not aware of that, especially membrane protein. But
is it possible to send some literature related to this?
Okay, please write to me or mail.
Yes.
Okay,
Yes,
it's not
yes.
easy, but the second one, whatever the work I did it personally, the membrane one, that deuterated lipid samples are per deuterated, that across the acyl chain length, they are readily available in Sigma Aldrich. Only thing is you have to pay for 1 gram of the lipid molecule, you have to pay close to 1 lakh or so. If you are rich enough, you can go and order it. Okay, within a month, you will be having those samples with you. But membrane protein, we need to, I do not know right now what is the current situation. Okay, we need to either collaborate with them. I don't know any other vendor is available right now.
Okay, sir.
To do that.
Thank you, sir.
Yes, thank you. Any other questions? I always took more time, 5 minutes extra, 10 minutes extra, sorry. Yes, any other questions? Yes.
Yeah, you can unmute yourself and ask. That is a more preferable way. Um,
Sabil, whether it is available for us to have these recordings?
yes, sir. Yes, sir. The
It is
recordings-
available to participants also?
Of course, yes, sir. Yes, sir. For the future reference, we are giving the recordings too, so they can watch
Okay.
it later too.
Okay, that's fine. And I hope we had a group of people from different background. Today I spend little more on physics part of that.
And it's really interesting. In fact, it is not the my domain. Still, the lecture is very interesting.
Okay, thank you. And
Yeah.
for all the audience, if there are any questions, please write back to us through Sabil or directly with me. Okay.
And one request to participants, if you can, apart from the technical questions, if you can say anything, you can unmute yourself and ask. And or else we have to wind up the session. So we'll wait maybe 1 minute. Yeah. And you can also tell your the feedback. That also will come. Or you can put it in the chat box too.
Yes, guys, you have been given option to scold me if you wish.
No, sir. It is a really very interesting talk. From last 2 days, we got very good the new concepts. So in depth, we had to go in the literature, and then we had to start in the new directions. So thank you so much for providing the new way of thinking with NMR.
Yes, I was little skeptical when Sabil talked to me that I am not a conventional NMR guy, as I mentioned it from last 20, 30 years. I am completely, 20, 22 years, I never recorded any of the NMR signal, or I have never seen any NMR spectrum as a function of chemical shift. Our entire work is only the line shape or relaxation time measurements. That's why I was little skeptical about how well I would fit into your theme of the workshop. I hope I really did not disappoint
No,
any
sir,
of
no.
you.
Yeah, we have received some new directions, so we will go in that direction.
Okay. Okay, if there are no other questions,
Yes, sir. We can then we can wind up the session. I guess there is no more questions. And thank you so much from the organizer side. You the continuously 2 days you spend with us, and majority of the participants are from chemistry background. The things are very new to us. However, there are a few physics people and biology people. Definitely, they are looking for this kind of lectures. Hope they also got some new insight, and as the Ashok sir said, a new dimension of their thinking. And thank you so much, sir.
thank you. Thank you very much.
So, dear participants, will be tomorrow at 7 o'clock. Thank you, sir.
Thank you.
Okay. Good night.
Okay, sir. Good night, sir.
Okay. Thank you, sir.